Okay, here's a solution to the AP style rotational dynamics question that you had for a homework assignment. And first we're going to read the problem and then I'll go through it. It says a pulley of mass 3m, circle the things that are important, and radius r is mounted on frictionless bearings supported by a stand of mass 4m resting on a table as shown above. The moment of inertia, that's the same thing as rotational inertia, of this pulley about its axis is 3 halves, or 1.5 mr squared. So they give you the I value for the pulley. That's this guy right here. Passing over the pulley is a massless cord, we're not going to worry about how much it weighs, supporting a block of mass m on the left side and a block of mass 2m on the right side. The cord does not slip on the pulley, so after the block pulley system is released from rest, the pulley begins to rotate. So then there's a couple blocks below that we're going to draw force diagrams for. So we've got some information there. We know the mass of the pulley itself is 3m, and this I value includes that 3m. So I'm not going to substitute the 3m in for the m because they already have the mass of the pulley factored in there. Because the pulley is, I'll just explain, the pulley is a disc, and the general formula for a disc is 1/2 mr squared. And if I substitute in the 3, that's where they get the 3 halves. It'd be the 1/2 3m r squared, that equals 1.5 mr squared. So that's where that comes from. Okay, so I don't need to substitute the 3m in there. All right, so let's go to the next page. Okay, so now we're going to, on the diagram here, draw and label all the forces acting on each block. So you've got the M block here, has the Earth acting on it, and the Earth's force is just the mass of the block times little g. And it also has tension in a rope going up. I'm going to draw that one longer because I know that the block is accelerating upward. So I want to make sure that I show that. And then I've got the 2m here has 2mg acting on it, and the same tension over here, and actually different tension. I better be clear about that. These tensions are not the same, so I better call it T1 and T2. And this is accelerating downward. And these two accelerations are exactly the same. So that acceleration and that acceleration are equal to each other because the rope is not slipping and there's no slack in the rope and it's not stretching at all. So we assume that if the object on the left, with mass m goes up 1 inch in 1 second, the object on the right would go down 1 inch in the same amount of time. So that's going to be the same acceleration. Okay, so use the symbols identified in part A to write each of the following equations for translational motion, and also for each one of the 2 blocks. Okay, so the equations here, based on Newton's second law. Remember, Newton's second law is F unbalanced equals mass times acceleration. Let's say for this block here, we'll be over there. All right. So we've got T1 minus mg equals ma. Over here, we've got, let's call it T2mg minus T2, because 2mg is a larger force than T2. So I know that's the larger of the two. I'm going to subtract T2, which is smaller, from the larger force, 2mg. That's going to equal 2m times the acceleration. Okay, so I've got 2 equations right there. And now I'm going to write the equation for the rotational motion of the pulley. Okay, analogous, I'm not sure why they use that word, but the Newton's second law equation for the rotational motion of the pulley. First I have to draw a force diagram for the pulley. So let's go to the next screen. All right, so the pulley is going to have T1 pulling on it over on this side. The pulley is going to have T2 pulling down on it on this side, with T2 being greater than T1. The pulley is going to have 3mg pulling down, and then the stand, I can't draw my vector long enough, has to have the sum of all those forces going up. I'll just say the force of the stand. I wouldn't call that a normal force because it's not a surface. I'm just going to call it Fs for the force of the stand. How about that? So that would be equal to all three of those going down. But, you know, there's only two of those forces that actually create a torque, because the force of the stand and the Earth's force, 3mg, pass through the axis of rotation here in the center. So those I just am not going to, you know, there's the axis of rotation in the center. So those I'm going to ignore those two forces, and I'm going to say the clockwise torque caused by T2 is going to be larger than the counterclockwise torque caused by T1, because I know T2 is going to cause this to rotate in this direction, and I'm going to also have an angular acceleration as well in the same direction. So the way I would write that is I'd say the sum of the torques are going to be equal to I alpha. Remember, that's Newton's second law for rotational motion. And the sum of the torques would be T2 times R minus T1 times R. So I'm calling this, even though it's a negative torque, I recognize that because it's going clockwise, it's the bigger of the two. So I'm just going to call that, you know, subtract the smaller torque, T1R, from the bigger torque, T2R. And then I set that equal to I times alpha, all right? And then we'll take that to the next page where we got a little more room. Okay, so I've got an equation now for the object in the rotational motion of the pulley itself. So I'm going to substitute in the 3/2 mr squared, that's the I value if you remember, times alpha, right? And I think that's all I need to do for that part of the question. Okay, so we're going to use this equation right here, and the two equations for each individual block, and we're going to solve for the acceleration of the two blocks in terms of these other variables, the r and the m, and so on. So if you remember the equations from the previous slide, T1 minus mg equals ma, and the other one was 2mg minus T2 equals 2ma. Okay, so I need to solve for T1 in this equation and solve for T2 in this equation and substitute them into these spots here. So I get rid of the T1 and the T2 variable, and then I'm going to have to substitute in for the rotational or the angular acceleration in terms of the linear acceleration, because the angular acceleration, remember, is equal to the tangential over r. We've used that a couple times now in our problems that we've worked out in class, and this represents the tangential acceleration of a point on the edge of the pulley, and that point on the very circumference of the pulley has exactly the same tangential acceleration as the linear acceleration of the two masses down here. So all these a's are the same. Okay, so let's go ahead and do those. So I'm going to solve this for T1. That's going to be ma plus mg. Down here, T2 is equal to 2mg minus 2ma. And all I did was rearrange those equations to get, here I added mg to both sides. I moved it over there. Here I moved T2 over here, and I moved the 2ma over here. Okay? So I substitute this in here for T1, and I substitute this in here for the T2, and then I will substitute AT over RN for that, all in one big equation down here. Okay, so let's do 2mg minus 2ma, that's the T2, times R, minus, here's the T1, ma plus mg times that R, equals, here's the rotational inertia of the pulley, and then the angular acceleration is A over R. Okay? So here's what's going to happen. I can divide both sides by R, because I've got an R term right here and here, so I can divide by R on this side, and that'll cancel that R out, and I will have R squared, so I can get rid of that R. This will become R squared. Well, that's going to cancel out with that R. So it turns out the radius completely cancels out, right? And now let's simplify this. 2mg minus 2ma minus ma minus mg. I got to distribute my negative sign there. So this negative sign makes both the ma and the mg negative, equals 3/2 ma over on this side. So a lot of ma's and mg's here. So I got to combine some like terms. I've got a 2mg and a negative mg on this side, so I'll subtract the 1 mg from the 2, and I just left with positive mg. I've got a negative 3 ma over here, because I've got a negative 2 and a negative 1 ma, so I'll combine those like terms for a negative 3 ma. When I add that to the right side, I'll get 3/2 ma plus 3 ma. So I'll do that right now. So I get just an mg equals 3/2 ma plus the 3 ma, which equals 4.5 ma, I guess, right? Which would be 9/4. 9/2, sorry, 9/2 ma. Okay, but I'm supposed to solve for A, and since I have mg on this side equals 9/2 ma, I've got two m's, or an m on each side is what I've got. I'll divide by that on both sides. So the acceleration is equal to 2/9 times g. That's the final answer. The acceleration of the masses, actually it's the final answer for this part. The acceleration of the masses are 2/9 of free fall acceleration. And they both have the same acceleration there. The last part of the question asks us to, to determine the tension in the segment of the cord attached to block M, that's on the left side, start with the equation for block M, which was T1 minus mg. That was the Newton's second law equation. And we now know that A is 2/9 g. All right, and we can solve for T1 in terms of m and g. So T1 equals ma plus mg, right? And then 2/9. Why do I keep drawing that way? Sorry, 2/9 g plus mg. So you've got an 2/9 mg and an mg. So you basically have 11/9. So it's kind of a strange number there. 11/9 mg is the tension. And that makes sense because that's in the form of a force. Mg gives us units of newtons. It's a little more than 1 newton. I mean, it's not more than, it's a little more than, like 1.2, a little less than 1.2, or a little more than 1.2 times mg is the answer. Okay, hopefully that makes sense to you. If it doesn't, please ask questions and let me know in class. Thanks.